Hello there, welcome to my video. My name is Atef Shalan. Today I'll be glad to talk to you about AVL tree data structures. After this session we will be able to describe AVL trees and tell the difference between AVL trees and binary search trees. We'll also learn some basic operations of AVL tree data structure. Some of these operations would require that we rebalance the tree, and we will learn how to balance the AVL tree after these operations. As a quick motivation to the topic, I would like to mention that we are in the era of big data, and trillions of records are created every minute using the search engines, customer transactions, social media. And of course, this amount of data needs to be handled by large database management systems that index this data and store them in secondary storage devices. That also brings the need for high-speed retrieval methods to fetch the data on these hard disks and do the other search operations, such as traversing data, maximum finding the minimum, insertion and deletion. Well, the problem with linear data structures, if we use them in this mechanism, is that they are costly. So the linear data structures would cost big order of big O of n to perform the basic operations that I just mentioned here. So that brings the need for some more efficient data structures, such as binary search tree, which is used for this purpose. Binary search trees can perform these operations using less complexity. A binary search tree is basically a binary tree which has mainly two nodes at most under every node. And the tree is mainly implemented as objects where these objects have some attributes such as key, data that we store in this node, left and right branch of that tree, and the parent of that tree. Well, as binary search trees, these trees should satisfy the binary search tree property. The property simply says that for every node in the tree, all the nodes that are on the right must have key that is larger than the key of this node, and all the nodes that are on the left must have keys that are smaller than this node. So if we look at this tree over here, we will find that the first one is really a binary search tree, because if you just follow every node, you will find that it satisfies the binary search tree property. If you look at the second one, it is also a binary search tree, while if you look at this one, you will find a violation because 5 is not less than 4, therefore this is not a binary search tree. Well, to search the binary search tree, we use this simple algorithm, which is mainly a recursive algorithm. The algorithm starts at the node, the root node X, and try to insert a key, try to search for a key K. First, it checks whether this X here has the key that we are looking for. If yes, then this is returned. If not, then the algorithm will keep searching on the left branch of the tree, trying to find the search key. Depending on the value of the key we are looking at, if it is smaller than the key of the node X, then the algorithm will fetch the left-hand side, or if it is larger, then the algorithm will search the right-hand side of the tree. Well, obviously, the algorithm takes order of big O of H, because the two recursive function calls over here simply dig down the tree. So if we start at the node X over here, next iteration of the recursive call will be either working with the 6 or 19, and so on it goes until it reaches the leaves at the bottom. So in all cases, the worst case scenario is that it reaches through the whole height of the tree. And of course, the first part here, the if statement, this is just a fixed or a constant time complexity of order 1. Well, just to practice how to search something here, we have these two calls when we search the tree for a key 9. So we have this tree and we are actually looking for 9. So simply the path will look like that. Based on the function, first the algorithm will check the x, and since we are looking for 9, then it is smaller, we go to the left. Then it compares with the 6. Now we are looking for higher. Then it goes to the right. Then again, 9 is higher than 7. It goes to the right. 9 is less than 13. It goes to the left until we find it. Well, we now try another example where we search for something that does not exist in the tree. Something like 5. This tree does not have this 5. So anyway, what happens is this. The tree starts, the algorithm starts at 15. And then it searches for 5. Then it goes to the left. 6 is larger than 5, again, then it goes to the left. 3 is less than 5, then it goes to the right. 4 is less than 5, then it goes to the right, and it finds nil at the end of the tree. Of course, this is going to be returned. So in this case, the algorithm works fine, and we notice that the algorithm takes order of big O of H. We do the same thing for insertion over here, and we have the algorithm. The algorithm is again simple. It starts at the top node or the root node of the tree and tries to insert a node Z in here based on the key value of this node Z. The algorithm has two main parts. The first part is a while loop, and the second part is just an if statement. The while loop, of course, here every iteration moves to the node that is child of the current node. So every time the algorithm, the while loop will again dig down into the tree until it reaches the leaf. Well, of course, the order of this while loop, after all, it will be of order h, where h is the height of the tree. Therefore, the order of the whole algorithm here is of order big O of h. So if, for example, we want to try the algorithm here, we want to insert something into this tree. We want to insert a node Z that has a key of 18. Again, we start by the root node. 18 is larger than 15. Then we go to the right. Then 18 is smaller than 19. Then we go to the left. 18 is larger than 17. Then we go to the right. In this case, the while loop will return the 17 as a parent node that we use later in the second part here to insert the node 18. Therefore, this will be the path, and this is where the node 18 will be inserted. Well, the cost of the operations using the binary search trees, as we know, we saw two algorithms, both of them take order of h. However, also the deletion minimum and maximum will take the same order, while the traversing will take order of n, where n is the number of nodes. Therefore, that's good, except for one thing, where the binary search tree can sometimes have disadvantage, where it does not really have good balance. In this case, the tree can grow dramatically to have a height that is equivalent to the number of nodes. Something like that. Imagine a case where you try to insert a tree, when you try to create a tree by inserting some data in ascending order or descending order. So we start by inserting 2, then 3, then 4, and so on. In all cases, we'll find that the tree is just a linear. In this case, this is the height of the tree, which is equivalent to the number of nodes. This is the worst case scenario of this binary search tree, and this is what makes binary search tree has this disadvantage over other more sophisticated binary search trees. Now we want to learn about more sophisticated binary search tree, which is AVL tree. AVL tree is balanced or semi-balanced or actually nearly balanced tree. The AVL tree will maintain a property called height balance property. This property maintains what's called height balance, the balance factor to be always something either -1, 0, or 1. Therefore, it will not allow the tree to have, for example, one side of one branch to be way higher than the other branch of the tree. It will maintain balance of the differences between the height of the right side and the left side of the tree. All right, now by maintaining this constraint over the AVL trees, now we will also limit the height of the tree to become always bounded by 2 log of n plus 2. Now this inequality is easy to prove by induction, by actually solving the relationship between the number of nodes in a binary in an AVL tree relative to the height of the tree, which is mainly a recursive equation that looks something like Fibonacci sequence. If you solve this equation, you will get that the height is always less than 2 log of n plus 2. Well, that maintains the balance of the tree. That maintains also the height of the tree to be at most of order log of n. Well, and this is the advantage of the AVL tree, is that it limits the h from going to the violation that it becomes very high or equivalent to the number of nodes. Now, we want to just look at these 3 examples of trees, and we want to see, are they balanced or not? They could be binary search trees, but we want to make sure that they are AVL trees. In order to do that, we want to see if they violate the height balance property or not. To do that, we have to calculate the balance at every node. Of course, the leaf nodes here will take a balance of 0, because simply we subtract the right side negative the minus the left side, which in this case 0 minus 0, that gives a balance factor of 0. If we look at the node 8 over here, we find that the right hand side is 1, the left hand side is 0. That means it is 1 minus 0, then the balance factor is 1. When we look at node 7, we find that it is actually 2, negative 2, which makes the balance of this node to be 0. Therefore, that whole tree is actually balanced. Now, we will find that this tree here is not balanced because, again, this is 0 at the leaf. Now, the balance of this one is -1, 0 minus 1. Balance of node 8 is -1, which is 1 minus 2. Balance of node 5 now is what? It's 3 minus 1, which makes it 2. That means this node 5 here will violate the height balance property, and of course that makes this tree is not an AVL tree. We'll notice that the third example is an AVL tree. However, we move forward. We try now the insertion algorithm over the AVL tree. Okay, so we have already looked at the insertion algorithm. We just now implemented over this tree, and we have example here, which we want to insert a node that has a key of 48. All right, so we start from node 44, which is a root node, and we compare to the 48. 48 is larger, then we go to the right. All right, now 48 is smaller than 78, then we go to the left. Then 48 is again smaller, then I go to the left. I found nil, then here where I can insert that node. All right, so I insert the node into the left side or left child or left branch of the node 50. Now let's try another example, such as inserting 54. All right, so we again start from 44. 54 is larger, I go to the right. 54 is smaller, I go to the left. 54 is larger, then I go to the right. Then 54 is smaller, I want to insert it here. All right, and this is how it comes after all. I inserted the 54 node over here. Now, that is okay, except for one thing, that when I recalculate the balance of this tree, I will find violation to the height balance property. Now, the node 54, which I just inserted, has a balance of 0. The node 62 has a balance of -1. Node 50 has a balance of 1, because this is 2 minus 1. Node 78 now has a balance of minus 2, because this is 1 minus 3 in this branch. Now the balance of this is negative 2. Node 44 now has a balance of 4 minus 2 on this side. That makes the balance of 44 is 2. Of course, these two nodes now violate the high balance property. Therefore, this did not become an AVL tree anymore. Well, what do we do in this case? Of course, we need to rebalance the tree. All right, in order to rebalance the tree, we have to, first of all, identify 3 nodes. We call them restructuring nodes, where we can restructure these 3 nodes and cause the tree to be rebalanced. Second, we restructure the nodes to do the balance. Well, first of all, I would like to identify these restructuring nodes. How to do that? Well, the algorithm is very simple. I just got the same figure from the running example here. Now I want to identify where are the 3 restructuring nodes that I can use to rebalance this tree after inserting the 54. Well, the algorithm is simple. Just to start from the node you have inserted and go up towards the root. When you hit the first node that is imbalanced, at this time stop and start marking this node. Call it Z. And then move down again 2 nodes to call them Y and X. Now these 3 nodes here are the 3 nodes that I have to restructure in order to bring back the balance of this tree. Okay, so now I could identify these 3 nodes. To do that restructuring or rebalancing of the tree, we will have just to look at this first algorithm. Okay, so I just had this simplified algorithm so that it becomes easy to understand that first part. We want to rebalance these 3 restructuring nodes that we have. In all cases, it doesn't matter really the structure of these 3 nodes. It could be LL imbalance, LR imbalance, RL imbalance, or RR imbalance. In all cases, it does not matter with the algorithm I'm going to show today. However, there is another method called rotation where it really matters to know how the imbalance look like. When it is LL imbalance, we solve it through rotation by 1R rotation. If it is LR imbalance, then we solve it by 2 rotations, first left rotation and then right rotation. However, today we talk about the restructuring method, which does not really take any benefits of that structure. So the method is simple. All what it does is just mark down these 3 nodes again as A, B, C, where A is the smallest, is the node with the smallest key, B is the node with the middle key, and C is the node with the largest key. After doing this marking, whatever the shape is of this imbalanced part of the tree, now restructure that part to bring B to the middle, C to the right branch or right child of the B node, and A to become the left side of that B node. So it becomes something like this, exactly. Now if you look at the 3 nodes over here, they are perfectly balanced. Same thing also happen when you have this structure. After all, you don't have to look at this structure when you implemented this algorithm. Now I just look at the middle point, which is B here. This is 20. I just put the middle point up and then put the one that is higher on the right and the one that's lower on the left hand side. That's it. This is a simplified algorithm. However, the general case should consider these 3 nodes, which could be in the middle of the tree, and of course they themselves has hanged subtrees coming out of them. Then the general case of the algorithm should consider these hanged trees as well. Well, it is again simple. All it does, or it just does extra, is considering these 4 subtrees. Well, the algorithm says that we have to mark the 4 trees that are hanging out of these nodes from left to right in order. So that first one should be T0, and then T1, and then T2, and T3. Well, if we have this shape in this case, it will matter. All what we care is, again, just to mark these trees from left to right in order. So T0 will be on the leftmost, and then T1, T2, T3, and then last it will be T3. And so on it goes. Well, after all, we just implemented the same algorithm. A, B, and C for the 3 nodes. B comes to the middle. A comes to the left, C comes to the right, and the trees just come down in the same order. Well, that is actually a very simple method, and it can be implemented easily on any tree. Now, we just come back to our running example. After identifying the 3 nodes that are used, that should be used for restructuring the trees, now we just want to rebalance these 3 nodes. Well, we notice now that T0 is this tree over here, which has a node 48. T1 is this one here, which has a node 54. And T2 is here, which is null or nil. And then last node, T3, is the node, node 88. So where is my A and B and C? Of course, now this is 78, 50, and 62. Which one is in the middle? It is 62. 62 should be in the middle, and then 78 will be on the right hand side, and 50 will be in the left hand side, and I get this this AVL tree, which is now perfectly balanced after doing this restructuring. Well, that is almost all what I want to say. Now I just want to run this quick example to create an AVL tree based on some list of numbers. So we just start by creating the first node 51, then we create the second node 54, of course 64. 64 is larger than 51, so I insert it on the right. Then I wanna insert 25, and it should go to the left of the 51. Well, so far it is going very easy. Now I wanna insert the 11, so it goes on the left of the 25. And I want to insert 8, it goes again to the left of 11. Well, here we have to stop, because when we calculate the balance of the tree, we will find that node 8, which is just created, takes a balance of 0. This node 11 now takes a balance factor of -1, because 0, -1, 0, -1. Again, node 25 takes a balance of -2, because it is actually 0, -2, and the negative and node 51 balance factor is 1 - 3, so this is now -1. The tree is imbalanced. I have to rebalance this. First step is to identify the 3 restructuring nodes. How I do that? Okay, I just inserted the 8, then I go upward towards the root node until I find or hit the first imbalanced node, which is now 25. And then I mark this node as Z, and then mark the next 2 nodes towards the bottom again as X and Y. Well, after doing that, now I know the 3 nodes I want to restructure, which is 25, 11, and 8. Which one is in the middle? It is 11. So 11 will act like B, 25 will act like C, 8 will act like A. I just restructure those 3, and I get the 3 now balanced. If I calculate the balance factor again for all the nodes, it will be 0, 0, 0 over here. And now the 51 is balanced because it is -1, which is acceptable according to the height balance property. Moving forward, now I want to insert the 85, which again will not make any difference. The 3 again is still balanced. Well, now I want to insert 50. Again, that does not really cause big of difference. The 3 is still balanced. Now I want to insert the 43. Of course, my insertion path will be like 43 is less than 51. Then I go to the left. 43 is larger than 11. I go to the right. Larger than 25. I go to the right. Less than 50. Then I go to the left. I insert to the left of the node 50. All right, I did, but the problem is the tree now is imbalanced, and I will notice if I go up here, if I recalculate the balance factor, that this is again, this becomes a 0, this becomes a -1, The balance factor of the 25 now becomes 2 minus 0, which is 2. Balance factor of this node 11 is now 3 minus 1, which is 11. Balance factor of the node 51 is now 2 minus 4, which is negative 2. Alright, I want to rebalance the tree. So first of all, I would like to identify the 3 nodes that are causing this imbalance. How do I do that? I go up towards the root from the node I just inserted until I hit the first node that is imbalanced, which will be actually 2. Then I mark this one as the first one in this restructuring node, and the next 2 will be the other 2 nodes that will be used to rebalance the tree. Now I identify these 3 nodes. All I want to do is just rebalance or restructure them. Which one is in the middle now? I have 25, 50, and 43. 50 is in the middle. 50 goes up, 25 goes to the left, and 43 goes to the right. Then it becomes, oh, 43 is less than 50. Well, so it goes like that. 43 in the middle, 50 on the right, and 25 on the left side. Well, last thing I want to insert now, the 14 to the 3. When I insert it, it goes in this location. Of course, this causes again imbalance at node 11 and node minus 2 and node 51. Of course, second step is to identify the restructuring nodes, which are 11, 43, and 25. Which one is in the middle? Now it is 25. Well, I put 25 up, 11 to be on the left, and 43 on the right. Of course, because now these 3 nodes are actually in the middle of the trees, I have to first of all find out the 4 subtrees of these 3 nodes, which is T0, T1, T2 to T3. And here they are. T1 is in the left, on the rightmost, and then followed by that was T0, and then T1 comes after, and then T0, T2 comes after, until T3 is at the leftmost of these 3 nodes. After identifying these 4 subtrees, now the job is easy. I just want to put the 25 up and 11 to the right, 43 to the left, the opposite, 11 to the left and 43 to the right, and just reinsert the trees back again in the same order. Well, I'm done with this example. Now the tree is balanced, and thank you very much for watching my presentation.